All right, so we just talked about this invertible matrix theorem here, which gives us a bunch of different equivalent results to a matrix being invertible. What we need to be able to do is verify that these really are all equivalent to each other. And we've proved some of these steps before, but we really need to establish the whole thing now. So we're going to do the proof of this. Right. And to show, when we're doing a proof where we're trying to show that we have a bunch of things being equivalent to each other, there's, we essentially have to be able to get from any number, any statement to any other statement. Okay? So this is going to kind of look like a grid almost. So the pattern we're going to do is we're going to sort of show that the first statement means the second is true. The second statement means the third one is true. The third one means that the fourth one is true. The fourth means that the fifth is true. The fifth means that the sixth is true. The sixth means that the first is true. And we're actually going to talk about how 4 and 7 are the same thing. So, since we make kind of a big circle here, we're able to say that, if we start at any number here, following these arrows, we can get to any other number. And that means that they're all equivalent to each other. All right, so let's start by showing that, I'll call this part A. So this will be A, B, C, D, E, F, and G. So let's start with A, which is that 1 implies that 2 is true. Okay? So 1 was that we assume A is invertible. Okay? Then, if AX equals B, then if multiply both sides by A inverse. To get, right, we get X equals A inverse B. All right? And, well, this is a unique statement, right, which is unique for each choice of B since A inverse is unique. Right? Because there's only one inverse, whatever we pick for B, this product A inverse times B, there's only one thing that can be. And therefore, this is your unique solution. All right, so that's 1 implies 2. How do we know that 2 implies 3? Right? Well, what we're going to do is, all right, since AX equals B has a unique solution, for any B, all right, for any B, we're going to choose B equals 0. All right, which would make this into a homogeneous system of equations. Okay? Then the unique solution is X equals A inverse times 0, which is just going to be 0, which is the trivial solution. Okay, so, oops, sorry, this was part B. of that equivalence. All right. So this means that x equals the 0 vector, so all of the x's equal 0. This is the only possible solution. And that's just what we call the trivial solution. When all the x values or all the variables are 0, that's just what we refer to as a trivial solution. Okay, so that's 2 implies 3. Let's look at the third equivalence, which is that 3 implies 4. All right? Now this one, it's actually not that bad to solve. But we have to sort of think about, we have to kind of take a step back and think about how we would solve the system. Okay? So, all right, so in order for ax equals 0 to have a unique solution, okay? In order for that to have a unique solution, we need to be able to reduce the augmented matrix A, comma, the 0 vector here, to the identity, comma, the 0 vector. Right? This is the only way. This is the only way for a system of equations to have one solution, is if we get the identity matrix over here. Okay? But since we now have the identity matrix over here, well, how do we reduce this to this, right? Well, we do this via row operations. Right? So, oops. But since we use row operations to turn essentially A into the identity here, we thus have, hence A is row equivalent to the identity. Right? And that's what we wanted, right? So again, if we can't reduce the left side of this augmented matrix all the way down to the identity matrix, if that's impossible, then this system of equations does not have a unique solution. It either has infinitely many or no solutions. Okay? All right, so that's 3 implies 4. Which one did I say we're going to do as part D here? Okay, so 4 and 7. All right. So why are 4 and 7 equivalent to each other? All right. Why are 4 and 7 equivalent? Well, remember here, how do I want to say this? So if A is row equivalent to the identity, right, to the n by n identity, maybe I'll even specify here in, right? If that's the case, then the row echelon form has n leading ones. Right? And vice versa. Right? Likewise, if if the row echelon form of A has n leading ones, then A has been reduced to the n by n identity. All right? Because we have a square matrix here. Okay? So remember, if we're in row echelon form, any column that has a leading 1 has zeros everywhere else. Okay? And if it has n leading 1s, which would mean the rank of A is n, then n different rows have to have a leading 1 in it. But if you think about what that means when you put it together, every column is made up of a single 1 and all zeros. Right? Every row has a leading 1 in it. Therefore, it must be the identity matrix. That's the only choice. Right? So these two statements are really the exact same thing. Being row reducible to the identity matrix is just saying that the row echelon form is the identity matrix. Okay. And if the row echelon form is the identity, that's the same thing as full rank, or rank n. Okay. So far we've shown that 1 implies 2. Right? So let me just kind of fill in here. So far, we have 1 implies 2, implies 3, implies 4, which is equivalent to 7. Now we need to start making our way back to 1. And this is where 5 and 6 are going to come in. Right, so this was part D, right? Yep, part D. So part E, we're doing 4 implies 5. Okay. So part E is 4 implies 5. How do we show that 4 implies 5? Well, if A can be reduced, we've actually proved this before, to the identity matrix, let E1 through EK be the required row operations. Okay? Then, the identity matrix is equal to EK minus 1, dot, 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 E2, E1, A. Right? That's what it means for A to be row equivalent to the identity matrix. Okay? But solving for A, we know that A equals E1 inverse, E2 inverse, dot, 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 EK minus 1 inverse, EK inverse. And since the inverse of an elementary matrix is invertible, or is elementary, we have A written as a product of elementary matrices. Right? Sorry, I should have set up here. When we say that these are the row operations, remember the way to write down kind of row operations done on a matrix here is we multiply by elementary matrices. So these here, these row operations are the elementary matrices. All right. All right, so we've now done 4 implies 5. Okay. Now we need 5 implies 6. All right. So 5, oops, this is F. 5 implies 6. Okay. So what I want to say here is recall that the determinant of E is not 0 for any elementary matrix. Any elementary matrix E. Okay? Remember that that's true. Okay? Let A equal the product of these elementary matrices. All right, so a product of elementary matrices. Okay? So, then the determinant of A is equal to the determinant of this product here. All right, so it's the determinant of this product of elementary matrices. But remember, if we're taking a determinant of a product, that's the product of the determinants. Okay? But what do we know? Well, we know that this isn't 0. We know that this isn't 0. We know that this isn't 0. And neither is anything in between. So this is not 0. Ta-da! We've now shown that the product, or sorry, if A can be written as a product of elementary matrices, then it does not have a 0 determinant. Right? In other words, the determinant is non-zero. All right, we're one step away now. I know this has been a long one here, but we're one step away from finishing this off. All we have to do is get back to 1. So we have to be able to say that a determinant not being 0 is equivalent to being invertible. Right? So this is G. 6 implies 1. All right, now this one, wasn't obvious here. Okay. So what we want to do is say, okay, so let B be the row echelon form of A. Okay? So, then we're in one of two situations. Okay? So then, either determinant of B equals 0, or determinant of B is not 0. Right? Actually, hold on. Let's take a step back from that. Okay? All right. So we have one of two things that can happen. Then either B is the identity matrix. Okay? Now, I want you to always remember here, A is an n by n matrix. So, when we put this into row echelon form, we either have to have the identity matrix, or B has a row of all zeros. All right, it might have more than one row of all zeros, but it has to have at least one. Okay? Well, if B has a row of all zeros, then the determinant of B equals 0, right? But since B is the row echelon form of A, we know that. All right, so since B is the row echelon form of A, B is equal to sort of E or EK dot 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 E2 E1A. All right. Right? Well, so since the determinant of each of these EIs is not 0, it follows that determinant of A must be 0, right? Because if determinant of B equals 0, oh, sorry. It follows that must be true since the determinant of B, which we're assuming is 0 here, if B has a row of all zeros, right? It's the product of all these things. Right? So if this is not 0, this is not 0, and this is not 0, then this one has to be 0. But in this case here, if we're starting with 6, we're kind of making we're making the assumption here that the determinant of A is not 0. Okay? So B cannot have a row of all zeros. Well, what does that mean then? Well, since B cannot have a row of all zeros, then B must be the identity, and this equation here, oops, hence we have this, and oh, sorry, oops, hence we have this, and EK dot 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 E2 E1 is the inverse of A. All right. So, I know this is a bit of a marathon video because we're trying to prove a big, massive theorem here, but I really want you to think about how, you can move between these different things here. But the really useful thing about this theorem here is, knowing why it's true and why it works is very important. But the incredible thing about this theorem is what it kind of allows us to say, right? We can, if we have a system of equations that has the same number of variables and equations, then all we have to do is take out the coefficients, put them in a matrix, take the determinant. If that determinant's not 0, then we know for sure there is only one solution. Okay? We also know that if a matrix is invertible, then, if we take the determinant and it's not 0, then we can break it down into these row operations. And more importantly, we'll have this rank nullity theorem a bit later that will sort of say, like, well, if the determinant is 0, let's say, then we know that it can't have full rank. And if it doesn't have full rank, we know that it's either infinitely many or no solution, right? So there's lots of really neat stuff here. But I'll leave it here before we go on too much longer. And yeah, see you in the next one.